What if the world you see around you, the chair you're sitting on, the light from your screen, even your own hands, what if none of it is real in the way you think it is? What if this solid, tangible reality is an illusion, a program that only renders itself into existence the moment you observe it? This isn't just a line from a science fiction movie. This is the kind of staggering question that gets sparked by a very real and very bizarre quantum experiment. An experiment so strange it baffled the greatest minds in physics, including Albert Einstein himself. It's an experiment that pulls on a thread of our reality, threatening to unravel everything we thought we knew. And if you follow that thread far enough, you end up staring at a mind-bending possibility that we might be living inside a sophisticated computer simulation. For centuries, we've operated under a simple assumption: the world is out there, independent of us. A tree falling in a forest makes a sound whether someone is there to hear it or not. It has a definite location, a solid form, a reality that doesn't need our permission to exist. This is the world of classical physics, the intuitive common sense world we experience every single day. But in the early 20th century, scientists began to peek behind that curtain. They dove into the realm of the ultra-small, the quantum world, and what they found shattered our common sense view of the universe forever. They found that at the fundamental level, reality isn't solid and certain. It's a hazy, probabilistic fog of potential. And the thing that seems to turn that fog into something real is us. The illusion of a solid world. To get a handle on how this is possible, we need to look at one of the most famous and, frankly, unsettling experiments in science, the double-slit experiment. The setup is pretty simple. Imagine a wall with two thin, parallel slits in it. On one side, you have a machine that fires tiny particles, let's say, electrons one by one. The electrons that get through pile up in a single band right behind the open slit. It's like firing paintballs at a fence with a single hole. Each electron is a single particle, so it has to go through either the left slit or the right slit. There's no other choice. Totally normal. Close that slit, open the other one, and you get the same result. A single band behind the second slit. On the other side, there's a detector screen that lights up wherever an electron hits it. Instead of two bands, the screen showed a complex pattern of many stripes, light and dark. This is an interference pattern, and the only thing we know of that makes a pattern like this is a wave. It happens when a wave passes through both slits at the same time, and the two new wavefronts interfere with each other. Where the peaks of the waves meet, they create a bright stripe. Where a peak meets a valley, they cancel out, creating a dark stripe. Now, if you close one slit and fire the electrons, you get exactly what you'd expect. So, logically, if you open both slits, you should see two bands on the screen, right? Just the sum of the first two results. How can one electron, all on its own, seemingly pass through both slits at once and interfere with itself? It was a result that flew in the face of common sense. It suggested that at a fundamental level, a particle doesn't have a definite location until it's measured. Until then, it's more like a wave of possibilities. But that is not what happens. When scientists ran the experiment with both slits open, what they saw was shocking. This seemed impossible. We're firing single electrons. They're tiny specks of matter, not waves spread out in space. The observer effect. Reality's biggest question mark. This is where the mystery deepens into something that feels like a glitch in the fabric of reality. The physicists who saw this pattern were stumped. Their next logical question was, okay, let's just see which slit each electron goes through. I mean, it has to go through one or the other. So they placed a tiny detector right next to the slits to record the path of each electron. They set up the experiment again. The electron gun fires. The particle travels toward the slits. The detector is waiting to see which path it takes, and this is the moment that changes everything. The very act of placing a detector at the slits, the act of measuring which path the electron takes, completely changes the outcome. The moment you measure, the interference pattern vanishes. It's gone, and in its place are the two simple, distinct bands we expected all along. The electrons go back to behaving like normal particles, going through one slit or the other, but not both. Let that sink in for a second. Proponents of the idea look at this and see something familiar. To save processing power, a video game doesn't render the entire world in full detail all the time. It only renders the area the player is currently looking at. They ask, is our reality operating on a similar principle of rendering on demand? Is the universe saving resources by not calculating a definite state for a particle until a measurement forces its hand? The universe appears to behave differently when it's being watched. When nothing is looking, a particle exists as a wave of potential outcomes. But the moment you measure it, that wave of possibilities collapses, and the particle settles into a single, definite state. It is important to note that the observer here doesn't have to be a conscious person. Any form of measurement or interaction that reveals the path is enough to collapse the wave. Now, this is where the simulation hypothesis comes in. Einstein's nightmare spooky connections, if that wasn't weird enough for you. Quantum mechanics has another trick, one that takes this strangeness to a cosmic scale. It is a phenomena Albert Einstein found so unsettling, he famously called it spooky action at a distance. Today, we call it quantum entanglement. You can separate these two particles, sending them to opposite ends of the galaxy. The instant you measure a property of one particle, like its spin, you instantly know the corresponding property of its partner, no matter how far away it is. The connection seems instantaneous, faster than light. Imagine you have a pair of particles that are created together and linked in a special quantum way. Now, to be clear, this doesn't mean we can send messages faster than light, but experiments have confirmed again and again that this spooky connection is real, and it baffled Einstein, who thought there must be some hidden variables or pre-existing information telling the particles how to behave. It turns out there aren't. Two characters might be on opposite sides of a huge map. To them, the distance is enormous, but to the computer running the game, their locations are just two sets of data in its memory. The distance is an illusion of the code. The processor can update both sets of data at the same time because, to the computer, they are fundamentally right next to each other. If our universe is a simulation, then space itself is just part of the program. The spooky action isn't an action traveling through space. It could be the underlying system updating two correlated variables. So how do we explain this? How can two particles, separated by millions of light years, be connected in this way? The simulation hypothesis offers a wild, but strangely neat, explanation. Think about a video game again. The simulation hypothesis is our universe code. When you combine these ideas, the simulation hypothesis starts to feel less like fiction and more like a legitimate philosophical question. Some thinkers point to other clues. The laws of our universe are described by elegant mathematical equations, almost like the universe is running on a kind of source code. A physicist named Melvin Vopson has even proposed a new idea called the second law of suggesting that information in systems behaves in a way you might expect from a system trying to optimize and compress data, like a computer running efficiently. On top of that, there's a theoretical concept that reality might be picked at the smallest possible level, the so-called Planck scale. Some quantum gravity theories suggest that space and time are not smooth and continuous. Instead, they might be made of tiny, discrete units, like pixels on a screen, creating the illusion of a continuous image. The idea was famously laid out by philosopher Nick Bostrom. He argued that one of three things is likely true. 1. Civilizations like ours go extinct before creating hyper-realistic ancestor simulations. 2. Advanced civilizations just aren't interested in running them. Or 3. We are almost certainly living in one. The logic is that if civilizations do create many simulations, then the number of simulated people will eventually dwarf the number of real ones, making it statistically probable that we are among the simulated. The counterargument is quantum mechanics just too weird to fake, but it would be a huge mistake to present this as a slam dunk. There's a powerful counterargument, and it also comes from quantum mechanics. What if the very weirdness of the quantum world doesn't suggest we are in a simulation, but actually proves we can't be? A 2017 paper by physicists Zohar Ringel and Dmitry Kovarezin showed that just to store the information required to simulate certain quantum effects on a small scale would require more bits than there are atoms in the observable universe. The complexity is just too enormous. The true randomness we see in quantum events is another issue. Computer programs are good at faking randomness, but many believe the universe's randomness is the real deal, something that can't be generated by an algorithm. So, while some see a rendered world, others see a world whose fundamental nature may be the ultimate firewall against being. Some physicists argue that simulating quantum phenomena is not just hard, it might be fundamentally impossible for a classical computer. From this viewpoint, the bizarre nature of quantum mechanics isn't a clever programmer's shortcut. It's a sign of a reality so fundamentally complex that it defies simulation. The questions thrown up by quantum mechanics are some of the most profound we can ask. They challenge our identity, our purpose, and the very nature of reality. We explore mind-bending ideas like this every week. If you want to keep questioning everything, make sure to subscribe and hit that notification bell. We are left at a fascinating crossroads. The foundation of our reality, quantum mechanics, shows us a world that behaves in ways that are hard to square with our everyday intuition and, in some ways, feels similar to how a computer simulation might work. Things like superposition and entanglements stretch our understanding and lead some to wonder about an underlying computational framework. And yet, that very same science also points to a level of complexity that might make such a simulation impossible. The clues are tantalizing, but the case is far from closed. So, I'll leave you with this question. If our reality is a simulation, who or what wrote the code?